Linear independence is one of the most important fundamental ideas in linear algebra. It tells us how vectors relate to each other and whether one vector can be built from another. Typically it's a set of vectors if none of them can be written as a linear combination of the others. So now we're going to be learning about span, I guess, eventually, but linear independence, basically you're going to be writing a whole summation of whatever vectors you're adding. Usually they're going to be vectors in a space, so if it's R2, if it's in R2, the most linearly independent you can have is C1v1 plus C2v2, two vectors. When it's R3, now we have three vectors. And these are all equal to 0. So this, we only get linear independence when C1 is equal to C2 equal 0, or equal to Cn is equal to 0. That gives us the linear independence, that all of the coefficients are the same, so that all the vectors, I guess, are different. If there is a solution where C1 and C2, well, maybe not equal to each other, but maybe it's equal to some constant, and this is equal to a constant, then V1 and V2 are linearly dependent, because then they're just combinations of each other. For example, if we have 1, 0 and 2, 0, you're just scaling the vector by 2, and you're getting a new vector. Technically they're different vectors, but they're just not linearly independent. So let's say we're in R3 and we have three vectors. Let's make them as a column vector. Let's say 1, 2, 3, 4, 5, 6, 7, 8, 9. And we want to find if they are linearly independent. The first thing we'll do is we can make it into a matrix, and a matrix can be composed of vectors, so we would have V1 here, V2, V3, and then we'll have the 0 vector here. So when we write this out, we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 0, 0. And then what we're going to do is we're going to row reduce it. I'll leave that as an exercise for the viewer. But we get 1, 0, 0, 0, 1, 0, minus 1, 2, 0, 0, 0, 0. So this shows us that x3 right here is a free variable. x1 and x2 are basic variables. And we can actually write like C1 minus C3 equals 0, C2 plus 2C3 is equal to 0. And we get these conditions: C1 is equal to C3, C2 is equal to negative 2C3. So then we can get a new vector C3 but that isn't really that gives us a but the main thing, I guess, when looking at linear independence is we go to the row reduced echelon form and we look at the pivot columns. We have two pivots, but we're in R3, so it must be linearly dependent. And that's basically it. So you take your vectors, put them into a matrix, row reduce it. If the number of pivots is less than the number of vectors, then it would be considered linearly dependent. Also, keep in mind that the row reduced echelon form also had these free variables, which means that there is a system of non-trivial solutions, which implies the vectors are linearly dependent. So I hope this helps. Have a good one. Basically, this means that the vectors v1, v2, v3 can be made from each other. They somehow can combine to make one another.